Hello everyone and welcome to a new Sega Mega Drive game dev tutorial. In today's lesson we're going to cover another much requested topic, and that is how to do background tile animations. And in order to do that we're going to have to learn how to manipulate the VRAM on the fly. And I know that's something that a lot of people would like to learn how to do. A special thanks to the Patreon supporters as always, and they can head over to there to download the code for today's class. Okay, now let's go through things step by step. So our starting point today is this simple demo where we've got a map and a parallax scrolling layer behind it. The reason I chose this green hill zone foreground is because we're going to animate these yellow flowers, so they're going to rotate around and around just like they do in Sonic. The starting code is very simple and straightforward, it's just things that we've covered many times before. What I want to do straight off is to take a look at the function we're going to be using to manipulate the VRAM, and that function is called VDP_load tile data. You can see here from the function description that it takes 4 parameters. The first one is simply the image, the tiles we're going to be loading into the VRAM, and they're going to be in the form of an image that we're going to load into resources.res. The second one is the index. Now this is what we're going to be focusing on to begin with, because it's very important to know how the VRAMs arrange. Only after that can we really start manipulating and changing it. The third parameter is simply how many tiles we're going to be changing in VRAM, and the final one is the transfer method, and for this we're simply going to choose DMAQ. You need to be careful here as there is another function with a very similar name, that is VDP_load tile set. But remember, that is the one we use when we want to load in the tile set for a level map. Thankfully the parameters it takes are different, so even if you make the mistake, you do a typo, you should realize your mistake pretty quickly. When loading in the level assets, both the background and the foreground, we create a variable called ind, and we make that equal to the tile user index. Now the tile user index is just an address in VRAM, and that's where SGDK wants us to begin writing the tiles, copying the tiles over for the levels. And you can see we start with the background map and we're loading the tiles from that, and then we shift the index, the ind variable, we shift it over so that when we come to write the tiles for the foreground map, we don't overwrite the background tiles. So this ind variable is just a way to keep track of where we are in VRAM at any given point. This final shift to ind, where I shift it after loading in the tiles for the foreground, isn't strictly necessary since we're not loading any more level assets after this, but it's something I did anyway for completion, but you could have deleted this final line without having any problems. Looking at the VRAM breakdown for the little demo we've made, you can see where the background tiles, the buildings, are loaded, and then you can see the foreground tiles loaded after it. What is a little confusing is we have 16 tiles before the background tiles. You can see these different colours, and they actually represent the first 16 colours of the palette. Now when it comes to messing about with SGDK, I tend to be very conservative, and I take the Chesterton's fence attitude to things where if something exists, it probably exists for a good reason. I shouldn't mess about with it too much. However, after talking to some people in the Mega Drive dev scene, they've all confirmed that it's usually safe to overwrite these tiles with your background tiles. Remember that I said that tile user index is the address in VRAM that we begin to write our background tiles. Well, if I subtract 16 from that, it means we're going to start writing the tiles 16 tiles earlier. And if I then save and compile, you'll see that those 16 tiles at the very beginning are now gone. We just start off right from the bat at the very start of VRAM writing our background tiles. While 16 tiles may not sound like a lot, we are very limited in VRAM on the Mega Drive, so any useless garbage tiles we should really get rid of. And just for fun, if I add 100 to the tile user index rather than subtracting 16, you can see in the VRAM debug screen now that we've got 100 tiles in between that little palette section, the 16 tile palette section, in between that and where our background tiles begin to be written. Now if you're anything like me at this point, you may be curious to know what would happen if you subtracted say 17 from the tile user index rather than 16. Well, after saving and compiling we get this result. And as you can see, it's pretty messed up. So we've obviously overwritten some data to do with the scrolling and the palettes, because we've undershot where we should be writing the tile data. So that's what's causing it to mess up. So it's probably for the best that we just change it back to -16. In the future, I will do a whole lesson on how best to utilize VRAM, little tricks that I've learned over the years. But For now, I just wanted to give you an understanding of how the VRAM addressing works. Earlier on, I spoke about how the ind variable stores the current address in VRAM so that we don't overwrite our background tiles with our foreground tiles. Knowing where the background tiles end and the foreground tiles begin to be written would be very useful, because when we're manipulating the VRAM and we want to start animating or changing tiles within our game, sometimes we might want to manipulate the tiles and do tile animation on the foreground. Sometimes we want to do it on the background. So that'd be very useful if, instead of overwriting the ind variable as we go along, it'd be good if we take those values, those addresses of where the background tiles are written and where the foreground tiles are written. It'd be good if we take those addresses and store them somewhere. Now, the best place to store them will be in an array. And since we're only storing the address of where the background tiles begin to be written and the foreground tiles begin to be written, that's just 2 addresses, so we just need to create an array with 2 entries. Feel free to call the array whichever name you like, just make sure it's descriptive enough so that you remember what it's doing. And make it a 16-bit number, a U16, as an 8-bit number wouldn't be sufficient for us here. The next step will be to insert this into our level loading code, just so we can keep track of the what the ind value is as we go along and as we load the background and foreground tiles. Remember that we can access any of the pieces of data in an array by using the index number. So since we've got 2 pieces of information, we can use square brackets 0 for the first piece of information and square brackets 1 for the second piece of information. So as we're going through our level loading code, you can see that we're storing the value of ind at the 2 different steps as we're loading the background and foreground tiles. Okay, with that done, we're now ready to start changing the VRAM on the fly. In order to practice doing this, I've created this 8 pixel by 8 pixel square image. And what we're going to do is we're going to take this single tile and we're going to replace one of our VRAM tiles with one of our level VRAM tiles, just so we get used to changing the VRAM data while the level is running. Please note that when we upload this into resources.res, we're going to upload it as an image, not as a sprite. The syntax we use is very similar to how we load the background image, but please note that the final 2 parameters in this case are none and none, not best and all as with the background. Now, as to why we're doing this, I'll cover that soon. Okay, now let's head back to our while loop and we're going to start using that function I mentioned at the very beginning, the VDP load tile data. The first parameter will be the tiles we want to insert into VRAM, and we're simply taking this information from that square image we just uploaded. And the next parameter will be the index in VRAM at which we start to write the new tile data. And for this, of course, we're going to use that array we just created. So first of all, let's start off by changing maybe a tile within the background image. So we're going to copy that and paste it into that parameter where we need the address in VRAM that we're going to save the new tile to. The third parameter is the number of tiles we're going to copy to VRAM. Now, since we're only using a very small image, as a single square tile, 8 by 8 pixels, we simply write 1 here. And finally, for the data transfer option, simply choose DMA_Q. Remember that first entry in our array is storing the address at which the background tiles begin to be written. So the very first tile of that will be the sky tile in the background. So if we replace that tile with our new little square tile, we should get this kind of result. Okay, so that's worked. So that very first tile in the background tiles, which was the sky previously, has now been replaced by our little square. And that of course has the effect of changing every single tile within the background that uses that particular tile. Going back to our tile loading code, if we were simply to add 1 to that index, then we should then hit the next tile along, not the sky tile, but the next one in the sequence of tiles that we loaded into VRAM for the background. And after saving and compiling, this is the result. So now we just have to check out where that tile is, that edge of the building tile. So we can see in VRAM debug, this has actually changed the second tile in the sequence now. Let's walk around and see if we can find it. And there it is. You can see just above Adam's head there, the corner. I think that tile's only used once in the background, but we can see that we've successfully changed the second tile of the background tile, the background tiles. If I add 8 instead of 1, you'll see that it should be the 8th tile which is changed now. So the 8th tile is obviously affecting that top of the rooftops here. If we check the VRAM debugger, you'll see that it is indeed the 8th tile that we've changed to that square. Okay, enough of changing the tiles in the background layer. Now let's change the tiles in the foreground layer, because that's after all is where our flower is located. To do that now, instead of using the first entry in our array, we're going to use the second entry in our array. So change the number in the square brackets from 0 to 1, and I'm going to do +0. We're going to try to hit the very first tile of the foreground like we did with the background to begin with. And fantastic, it's working fine. So the very first tile in the foreground layer is basically the fully transparent tile, which lets you see completely into the background. So you can see all those, instead of being a transparent tile, they have now been replaced with this square that we created. And if you look closely, you'll see that square just right where the foreground tiles begin to be loaded. Adding 1 should move on to the next tile being changed, so let's check it out. And you can see now that it's the top left hand corner of the tree leaf, which now has been changed to the square tile. So remember, we just changed one single tile in VRAM, and we can change all instances of that tile within the foreground layer or background layer. So I hope you're all beginning to understand how to manipulate the VRAM on the fly, but now how do we change that flower tile? You can see here that I've managed to locate the top tiles of the flower in VRAM. I'm looking for the next row of flower tiles, but it can be quite hard to see and to have to count where each section of the flower begins and then maybe use that function multiple times to get all the different flower sections to change will be very difficult. So I have a much better way of doing this, so let's check that out now. What we need to do is to open up our foreground in Sprite and then activate the tiled mode. Sprite generates the tile set in much the same way as SGDK does as we load the level map into it. So it searches from top to bottom, left to right, and then it assigns an index to each unique tile in the tile map. If we take a close look at the flower, we can see it is made up of 16 different tiles, but is split into 4 different sections by the tile set. So we have the top 4 right next to each other in the tile set, but then there's a gap, and then you have the next 4, then the next 4, then the next 4. The very first part of the flower in the tile set, the top left hand corner, is the index number 38. So if we add 38 and save and compile, we should see that top left hand corner being replaced with our little square tile. And you can see here that that is indeed the case. Now we could create 4 different graphics, each with 4 tiles, and then work out where in the index each of these batches of 4 tiles lay, and we could call the function 4 times, but that's a bit awkward. So what's a much better solution is we can change and manipulate how the tile set is loaded into SGDK so that all of the tiles for the flower are contiguous. So they start maybe at the index 1 and then go on to all 12, all 16 rather, tiles are right next to each other. Then we only have to create one flower graphic, the alternate flower graphic, and we only need to call that function once. You can see here that I'm beginning to move the tiles of the flower in our tile set so it's in position number 1. So we can't use the index 0 because Sprite reserves that, but I can move the top left hand corner of the tile to tile 1 in the tile set. So when I do that, you can see now that is at index number 1 instead of 38 where it was before. I'm going to repeat this process for all the other 15 tiles within the flower image. So I'm going to keep repeating. Of course, you can grab more than once. You can grab 3 and 4 at a time, as long as they're next to each other, and you can just gradually move them. Now each time I move a bunch, I'm going to need to, the little button pops up which says remap. So you're going to have to click that to remap it, just to tell Sprite that you don't want to change the level map image yourself. You simply want to change the order in which the tile set is written. Okay, so that's all 16 tiles of the flower rearranged within the tile set. So now they begin at 1 and they're all within one row. They all follow one after the other. So that means we only have to call the function once. We only need one image to replace them with of 16 tiles, and we can just change it all in one go. And the tree tiles, which used to be 1, 2, 3 and 4, have now been shifted along in the index 2. Unfortunately, merely making this change in Sprite doesn't change what's happening in SGDK. And now up until now, when we've been loading in the tile set and the map for the foreground, we've been using the same file, and we've been leaving it up to SGDK to do basically the same job that Sprite does, where it goes from top to bottom, left to right, and it collects all the unique tiles and it ignores any duplicate tiles. Instead of doing it this lazy way, what we need to do is we need to export the tile map that we created in Sprite and have SGDK use that to load the tile set instead. When you do this for the very first time, it might look something like this. So what you need to do is you need to change it to packed, that option to packed instead of in a long row. Not because it makes a difference in HTTK, it doesn't, but just because it's easy to look at for us humans. And you need to click the open sprite sheet button too, and then you can actually export it and open it. Okay, great. So now we have a tile set, and as you can see, it's exactly the same as we had it when we arranged it like this. So we've got the flowers, the flower tiles all next to each other at the very top. Now we can simply save it as usual, and as always make sure it's a PNG and make sure the color mode is set to index and the palette's okay, and then we can import it into SGDK in the normal way. So when creating the tile set for this level, we're going to actually use this tile set we just created, and you can leave the level map as before. Just to check that our new tile set is working, change that plus 38 to plus 1. And now it should change the same part of the flower as it did before, but now of course we've much more conveniently got the flower tiles all bunched up to the very beginning of the tile set. And you can see it's all working great, so that top left hand corner of the flower has been changed to a weird little tile, and if we check the VRAM debug, you'll see that all the flower tiles are all at the very beginning of the foreground tile set as we arranged in Sprite. Now instead of just changing that silly little tile, I think we're ready to do the flower animation. There's only 2 frames in this animation, the original as in our level map, as well as this other one which we're going to transfer into the VRAM as the level progresses. You can see that I've already imported it here, and just with the little square, make sure the last 2 parameters are assigned as none and none, and again it's going to be an image, not a sprite. Now back in our while loop, we need to make some changes. So first of all, instead of using our square, we're going to be using our flower image. So we're going to change that. We can keep it as +1 because it's going to be from the first index and it's going to do it from there. But instead of using just one single tile in the third parameter, we're going to change this to 16 tiles because of course the image itself has 16 tiles. And this is our result. If you look closely, you'll notice that the flower has changed to the next position, so it's got the vertical kind of spikes rather than the diagonal spikes. And if we check the VRAM, we can see that it has indeed been changed there too. In resources.res, I'm going to simply upload a new flower image, and this is just the original image as it appears in our level map. So because we want to change it from the second animation back to the first, back to the second, back to the first, so it looks very dynamic. Since we need this animation constantly changing back and forth, I think the best way is to create a timer. I think it'd be good if the animation may be changed every second. So every 60 frames, we're going to have the animation change. You can make it quicker or slower if you want. I'm using an U16, a 16-bit integer here. I could probably get away with an 8-bit one since we're not going to be counting up to 255. But I often find that when creating timers, later on I end up changing the code so it exceeds 255, and then I forget that I made it an 8-bit number and it creates stuff which I think are bugs, but really it's just the fact I'm using an 8-bit number. So I'm just using a 16-bit number here, but feel free to change it to an 8-bit number if you're sure that you're not going to go for 255. Then at the bottom within the while loop, we're going to use some if and else if statements just to iterate through the timer, and then once it hits 60 seconds, we'll change it to one of the flowers animations. So when it hits 120, we'll change it to the other animation, and then we'll set the timer back to 0, and we continue counting up one by one by one. I think I used similar code when we did the palette swapping, the palette animation, where we did the Shinobi waterfall. So I think the code should be familiar to you, so I won't explain it too much here. And of course, don't forget to change the name of the images if you're doing some copying and pasting like I am. And don't forget to set the timer back to 0 in the second if statement, just so we can go back to 0 and then go up to 120 again. After saving and compiling, we'll get this result. So you can see that the flower is now moving every second, so every 60 frames we have the animation, and you can see that taking place within the VRAM too. Now when loading our flower images into resources.res, I warned against using any compression, writing all in the final parameter, and that's because the result will look like this. The image we use, which replicates the flower as it appears in the original level map, appears fine, but the other one is all messed up, it's all very glitchy. Looking at how this is playing out in VRAM might give you a clue as to why. And if we take a closer look at that second animation image within our sprite, you'll notice that the top left, top right, bottom left and bottom right hand corner tiles are all blank. So they're all duplicate tiles. So if you use any compression by using all as the final parameter, it means it's only going to load these tiles into VRAM once. When we then go to load that tile information into our function, which changes the VRAM, it means the tiles are going to be out of order and there's not going to be enough of them, so it's going to appear very glitchy. So what we need to do is, when doing this kind of tile animation, we need to select none so that there's no compression, so that the SGDK will load every single tile into VRAM even if there are duplicate tiles. This is also the reason as to why in the original level map I had the flower originally in this position, because it has the full 16 unique tiles, whereas if I started it with the second animation flower, then there wouldn't be enough tiles. It'll create problems when we try to rotate the tiles in and out. In today's lesson, we tied the changing VRAM to a timer, so at certain times the VRAM changes, which creates this nice animation. But there's also another use case where if you want to create a very large level with lots of detail, with more detail than could normally fit into the Mega Drive's VRAM, you can make it so that the changing VRAM is tied to the player's position in the level. So as the player explores new parts of the level, maybe you can discard, you can overwrite the certain VRAM tiles which are not appearing on screen at that particular time, and you can load in new tiles on the fly. Using the method that I taught you today, doing that is possible, but would require some careful planning with how the tile set is set up. However, Shannon Burt of Lufterheit fame, who is now working on the Sword of the Apocalypse game 2, for that game, he's created this much more robust and much more sophisticated algorithm, which seems to be constantly changing the tiles used on the fly depending on where the player is appearing in the level. If I ever manage to work out what kind of black magic he's been doing to create this effect, then I'll be sure to do a tutorial at some point in the future. There is a situation which we're going to come across in the not too distant future in which the method we studied today is not going to be useful at all. When we come to do our Alex Kidd in Shinobi World remake, we're going to come across rooms like this, which have lots of destructible blocks. The Mega Drive couldn't display this many sprites without lots of flicker, let alone the Master System, so these blocks are obviously done on the background layer. Using the code we created today, if you were to destroy one block, then all the blocks would disappear at the same time. So we're going to have to put our thinking caps on and create an alternative solution. The RoboZ, who is doing the Mega R-Type port for the Mega Drive, did manage to work this out, so it's definitely possible, we just have to work at it. Okay, so that's about it for this video. Thanks very much for watching, and if you like this kind of content, don't forget to subscribe.
I'm interested in this.
And if you'd like to support my work further and get early previews of what I'm up to, then I have a Patreon account and any support is much appreciated.
You won't go unrewarded.
Until next time,
farewell.